Hey guys, and welcome back to my science studio. In the previous lesson, we talked about the law of conservation of mass and how to balance chemical equations. And if you haven't watched that video yet, I highly recommend checking it out first because it pretty much lays the foundation for today's lesson. But in this video, we're going to start exploring different types of chemical reactions, beginning with combination, also called synthesis reactions, and decomposition reactions. And you see, at their core, these two reaction types are essentially opposites of each other, and their names actually tell you what's going on. So without further ado, let's just jump right in. But before we differentiate between the two reaction types, there are a few symbols I want you to be comfortable with when reading chemical equations. The S means solid, L means liquid, G means gas, and AQ means aqueous, which means the substance was dissolved in water. So these symbols essentially tell us the state of matter that an element, compound, or molecule is in. And it's a very important part of a chemical equation. Okay, what is a combination reaction? Well, this is when two or more substances come together to form a single product. Hence, combination, they combine. The general pattern looks like this, where you have A reacts with B to produce AB, where A and B can be elements or compounds, and they combine to make one new compound. Let's take this example. Hydrogen gas reacts with oxygen gas to produce liquid water. In this reaction, hydrogen is your A, oxygen is your B, and water is your AB, the single products formed when they combine. That's a combination, a reaction where simpler substances come together to form something more complex. But a decomposition reaction, that's the opposite. You see, instead of building something up, you're breaking a compound apart. The general pattern looks like this. You start with AB, and that produces A reacting with B. So you're starting with one compound, and you're breaking it down into simpler substances. So using the same example as we did before, if you now take liquid water and break it apart, it decomposes into hydrogen gas and oxygen gas. So it's the same substances, just running the process in reverse. So a quick little side note, like some big picture thinking here. You see, chemistry is all about change, either physical or chemical. And when a chemical reaction happens, scientists look for clues that tell us a change has occurred. And some common signs include a temperature change, a color change, the formation of a gas, or the formation of a solid, called a precipitate. In combination and decomposition reactions, we're really tracking how atoms are either being grouped together or pulled apart to create something new. And here's a question I want you to think about on your own, and we will revisit this a little later in this video. Which type of reaction do you think requires more energy to input from the start? Is it bringing substances together in a combination reaction or breaking a compound apart in a decomposition reaction? Okay, now let's walk through one example of each reaction type so you can see this in action. For this first example, I'm going to give you the word equation. For my students, I'm not really expecting you to predict products for combination or decomposition reactions, but instead I want you to recognize the reaction type and write it correctly from words. Now, if your teacher or professor does ask you to predict the product, please feel free to comment below and I'd be super happy to make a video for you guys on that. Okay, so here's the word equation I got for you guys. We have solid magnesium reacts with oxygen gas to produce solid magnesium oxide. So step one is identifying your reactants, right, what you're starting with, and your products, what you're making. So solid magnesium is Mg, and you have to write the solid in parentheses symbol to denote that magnesium exists as a solid. And honestly, guys, all metals for the most part exist in their solid state, with the exception of, for example, mercury or Hg usually likes to exist as a liquid in room temperature. But anyways, I digress. Your other reactant is oxygen gas, which exists naturally as O2. It's a diatomic. And if you remember from my lesson where I talked about the periodic table and the 7 diatomic elements, there's a great mnemonic to help you remember them. It's have no fear of ice cold beverages. These exist as 2 atoms naturally bound to itself. And you must denote that in the formula. That's super important. This is a very common test trap. So always pay attention when the word gas is used. So if it's oxygen gas, it's O2 with the G in parentheses to denote it's a gas. If it's chlorine gas, it is Cl2 gas. If it's fluorine gas, it's F2 gas. So just keep that in mind, because if you don't include the 2, then your balancing will be totally off. Now let's write your product. The problem is saying that we're making solid magnesium oxide. Magnesium is in group 2 of the periodic table and will always bear a +2 charge. And oxygen will form a -2 charge. So when we cross the charges, they end up canceling each other out, giving us MgO. And just as a little side note, you guys, anytime you have the opposite charge but same magnitude, they're going to end up canceling each other out, and you get a 1-to-1 ratio for the subscripts. So a +1 and a -1, a +3 and a -3, they'll cancel out. But anyways, so now putting it together, we can make our skeleton equation, which will say Mg, solid, reacts with O2, gas, to produce MgO, solid. Now we can balance. On the left side, on your reactant side, we have 1 Mg and 2 O's. On the right side, we have 1 Mg and 1 O. So the oxygens are not balanced. So we can add a 2 as a coefficient in front of the MgO. And that 2 will distribute to the O, but it'll also distribute to the Mg. So now that we have 2 Mgs on the right, we have to make that balance with the left because it's off. So if we add a 2 in front of the Mg on the left side, now our balanced equation reads 2 Mg reacts with O2 to produce 2 MgO. And you guys notice how we started with 2 reactants, right? A plus B, and ended with 1 product, your AB. That's how we know this is a combination reaction. Now let's look at a decomposition reaction using this example. And it reads, solid calcium carbonate decomposes when heated to form solid calcium oxide and carbon dioxide gas. Well, first, let's identify what we're working with. And our reactant looks like it's calcium carbonate. And this is made up of calcium, which is in group 2, so it'll always bear a +2 charge. And carbonate, if you remember from my lesson on oxyanions, this is a type of polyatomic ion, meaning many atoms bound together, and it's charged, in this case it's -2, and it has oxygen in it, hence oxyanion. Anion means negative charge. And this specific oxyanion is called carbonate. But anyways, when you cross the +2 and the -2 charges, they end up canceling each other out, giving us CaCO3, solid. Now, earlier, I asked you guys a question to think about. And I asked, which type of reaction do you think requires more energy input? A combination reaction or a decomposition reaction? And the answer is a decomposition. You see, for the most part, when you break something apart, you need to put energy in. And that energy might come from heat or sometimes electricity, but either way, energy is needed to separate particles that are already bonded together. And because this reaction requires energy, we're going to show heat by writing a small triangle above the arrow. That's showing that the calcium carbonate is being heated to form the products. And speaking of which, let's write our products. For calcium oxide, we have Ca with a +2 charge and oxygen is a -2. Crossing the charges, they end up canceling each other out, and we end up getting CaO, solid. And carbon dioxide, this is a covalent bond, hence the prefix di in front of the oxide. So when we write it, we just write one carbon. Remember, the word mono is never used for the first name. And we write two oxygens present here. Hence CO2, gas. So our skeleton equation should read CaCO3, solid, yields CaO, solid, and CO2, gas. Now we can balance. Keep in mind that even though we have carbonate, which is a polyatomic, it's been split. So the oxygen has been split in two. So I wouldn't recommend to write the CO3 together just for this example, but keep that in mind for later examples. And if you're not sure what I'm talking about, definitely check out my last video on balancing, and I gave you a really neat trick for polyatomics. But anyways, so on the left side, we have one Ca, we have one C, and we have three O's. On the right, we have one Ca, one C, and we have three O's, two from the CO2 and one from the calcium oxide. And everything is actually already balanced, so no coefficients are needed here. And this reaction is a decomposition because notice how we start with one compound, your AB, and it gets broken apart into simpler substances. And notice that energy was required to make that happen. All right, now I want to give you a chance to fly a little solo here. So for the next two questions, I encourage you to pause the video and give them a try on your own. And as you work, make sure you write the chemical equation from the word equation, balance, include the correct states of matter, and identify whether it's a combination or a decomposition reaction. When you're ready, press play and we'll go through them together. So the first problem reads, sulfur trioxide gas reacts with liquid water to form aqueous sulfuric acid. Let's start by writing the formula. Sulfur trioxide is a covalent bond, so we write SO3, the 3 telling me that I have 3 oxygens present, hence the prefix tri. And it's a gas. Water is H2O, and it exists as a liquid in this case. And sulfuric acid, if you remember my lesson on oxyacids, this is an oxyacid. It comes from the sulfate ion, which is SO4 with a -2 charge. So because it's acidic, you're going to add a hydrogen ion in front of it, crossing the plus and the -2 charge. You end up getting H2SO4, and you write the aqueous symbol next to it. So now writing the skeleton equation, we end up getting SO3 gas and H2O liquid yields H2SO4, aqueous. And right off the bat, I can tell this is a combination reaction because I have 2 reactants forming one product. Now we can balance. On the left side, we have 1 sulfur, 2 hydrogens, and we have 4 oxygens, 3 from the SO3 and 1 from the H2O. And on the right side, we have 1 sulfur, 4 oxygens, and 2 hydrogens. And I don't know about you guys, but looks to me like everything is already balanced, so we're good to go on this one. Okay, let's try this last problem. When heated, solid magnesium hydroxide breaks down into solid magnesium oxide and water vapor. And the phrase when heated and even breaking down, those are huge clues. I mean, energy is being added here, things are being broken down. That rings a bell that this is a decomposition reaction. So now let's write the formulas. Magnesium hydroxide. Well, magnesium is Mg2+, and hydroxide is a polyatomic ion that takes the form OH with a negative charge. So the formula, crossing the 2+ and the -1 charge, gives you MgOH, and you have to write the parentheses around the OH because that 2 subscript came from the magnesium. That tells me I have 2 hydroxides present. And it's a solid because the question says so. And magnesium oxide, which is one of your products, Mg is +2, oxygen is -2, so when we cross the charges, we end up getting MgO, also a solid. And water vapor is H2O, that exists as a gas. Now writing the skeleton equation showing heat, we get MgOH2, solid, yields MgO, solid, and H2O gas. And you know what, guys? I think we're good. We have only 1 mg on the left, 1 mg on the right, 2 O's on the left, 2 O's on the right, 2 H's on the left, 2 H's on the right. Yep, we're balanced. And you see, since we started with one compound breaking apart, this is clearly a decomposition reaction. Okay, so why does all this matter? You see, these reaction types aren't just classroom ideas. They happen all around us. And a common combination reaction is iron rusting, where iron reacts with oxygen to form iron oxide. And a common decomposition reaction is hydrogen peroxide breaking down into water and oxygen. The same reaction used in hair bleaching and wound cleaning. You see, guys, chemistry is constantly building things up and breaking things down, and understanding these patterns helps you make sense of the world. Thank you guys so much for watching. If you found this video helpful, please don't forget to like and subscribe to my channel. If you'd like more practice problems on identifying reaction types from word equations, please let me know in the comments below. And be sure to check out my community page for weekly practice questions. In the next video, we'll be diving into combustion reactions, including both complete and incomplete combustions. But until then, happy studying!